Hello, statistics students. We're going to play around with some more probabilities ideas. In this case, we're going to play with independent events and conditional probabilities. So let's go here. So independent events are events that do not affect each other. So for example, I have two dice, Fred and Charlie. Now, Charlie rolls, and let's say he gets a 1. Now, Fred, although I've named him, really doesn't know about Charlie, and Charlie's roll does not affect what Fred does. So the probability of Fred getting a 6, knowing that Charlie got a 1, doesn't change anything. So again, so if I write that down, the probability that Charlie gets a 1, oops, no, I wanted to do that backwards. The probability that Fred, gets a 6, knowing that Charlie got a 1, that Charlie got a 1 doesn't matter to Fred. He's going to roll, he lands on a 6, it just happens that way. That's the same as just Fred getting a 6. So that knowledge doesn't change anything. If the knowledge of something doesn't change an event, that means the two events we're talking about are independent. So the probability that Fred gets a 6 is 1 out of 6, regardless of what Charlie gets. Okay, independent events. So events, again, are independent if one does not affect each other. Coins are a good example. One does not affect the other. And we use this, the vertical bar means that we know something. So again, in English, for my mother, I would say this is the probability Fred rolls a 6, knowing that Charlie rolled a 1. That knowledge does not change a damn thing, okay? And that's independence. And independence comes up a lot with conditional probabilities. So just some reminders about conditional probabilities. The probability of A happening, knowing that B happened. Okay, so again, the focus is the probability of A, but we have this knowledge about B. That's always equal to the probability of A and B happening divided by the probability of what we know, B. Okay. Another way you could think that is N is usually to count stuff. So the number of ways A and B can happen together divided by the number of ways B could happen. Okay. So another example would be, what's the probability that Fred gets a 6, knowing that he's going to get an even number? That totally changes things. I know there's going to be an even number. That changes my universe. So my denominator is going to be different. Okay. So instead of having Charlie get a 1, let's say that we know Fred gets an even number. So now my universe of things that can happen, let's write it up here. There's only 3 even numbers to choose from. The one I want, the favorable one, is the 6. So that would give me a 1 out of 3 chance that that would happen. So again, knowledge can change things sometimes. It doesn't always. So if events, so another way to look at that rule, it's also called the multiplication rule. And to turn a division to a multiplication, we just divide the denominator to the other side. So I'm just going to state that in reverse order also. So the probability of A and B is equal to the probability of A knowing B times the probability of B when we reverse that idea about having a condition. So that's what's called the multiplication rule. Now, if the events are independent, that means this knowledge is useless. So if we have independent events, the probability of A given B is just the probability of A happening. And so that changes the multiplication rule. So that sometimes, if you have independent events, that the probability of A and B happening happens to be the probability of A times the probability of B. And so we'll always have to consider when we have an and involved, if it's not obvious, or depending on the information we're given, we might have to consider this rule and whether they're independent or not. Just depends on the situation. So let's look at another example. Let's suppose we're playing cards again, and I wanted to, let's see, find the probability of getting a heart knowing that I have a red card. So we have a couple of different ways to do that. I could just consider counting. So I know I have a red card. So that completely changes the universe that I deal with, that knowledge. So if I know I have a red card, that means I know there are 26 cards to deal with. Now, of those 26 cards, I'm hoping I have a heart. Well, 13 of those 26 happens to be hearts. So the knowledge of having a red card does affect. So that means red and heart are not independent of each other. That the knowledge changes things. Now you may be thinking, that sounds like mutually exclusive. Well, they're two totally different ideas. Okay? Independent and mutually exclusive. You can have one without the other. Sometimes you have neither, sometimes you have both. It just depends on the situation. Alternative way to do that is to find the probability of having a heart and a red card and divide by the probability of having a red card. So let's do it that way just to check the formula. Okay, so I want a heart and a red card. Okay, so let's see. I want heart. Well, these are my hearts and they happen to be red. So that's a 13 out of 52 probability. Divided by the probability of being red, well, there's 26 out of 52. And if you remember to do division with fractions, you have to multiply by the reciprocal of the second fraction. So we get 13 over 52 times 52 over 26. And the 52s are kind enough to divide themselves out. And so I get 13/26, which you could reduce to a half or 50% if you want. Right, so there's multiple ways to deal with these situations. You can just look at your knowledge, realize that changes your universe, the total amount of possibilities, right? Knowledge changes stuff, and then look at what's favorable for you in that situation. Let's try another one with dice. So let's see, new screen. And we were playing with dice, or I was playing with dice the other day. Here we go, coins and dice. And let's snap that into my window. All right, so I have these two dice that I'm going to roll. All right, so let's say this guy up here is Fred, and this guy right here is Charlie. That's how I spelled Charlie before. And then I'm going to add them up, right? So I want to look at the sum. And so what I'm finding is there are 36 possible sums or possible outcomes. Now you might say, well, really, there's only 11 sums, right? Because you got the 2 and the 3 and the 4 and the 5 and the 6 and the 7, the 8, 9, 10, 11, 12. But the problem is they can happen in different ways because Fred could get a 2 and Charlie could get a 3 for a 5, or it could have been the other round. Charlie could have got the 2 and Fred could have got the 3 for a 5. Those are two different scenarios. And so what we're going to see is that we're more likely to get a 7 because there's 6 different ways that can happen. So the probability of having a sum of 7, again, sums are what we're looking at, would be 6 out of 36. The probability of getting a 2 as a sum, there's only one way that can happen out of 36. So there are 11 sums. There's 36 different ways those sums can happen, and so some are more likely than others from rolling 2 dice. So we need to know that. That's important information. So let's look at some options. Let's say, what is the probability of rolling an even sum and let's see, even and a sum that is greater than 6. So I want to look at those two together. Let's see. So things to think about. Are they independent of each other? Does does knowing you have a number greater than 6 affect being an even number? Well, yeah, because that would exclude a 4 and a 2. So that knowledge is important. So these are not independent. And so I definitely have to consider that. And is an intersection, so there's a couple of different ways we can do that. So we'll look over here, what are our even numbers? So let's highlight those. Even sums are this one, and that 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 one. Okay, so those are my even sums. So what is that? 1 and 3 and 5 and 5 and 3 and 1 is 18, I think, possible even sums there. Let's look next, oops, I want the highlighter, at being greater than 6. Okay, greater than 6. Well, 6 is not greater than 6, is it? It's equal to 6. So that means I have these guys here and these guys here. So those are my options. So we're going to break this up in a couple different ways to play with that formula. So it looks like there are 5, 6, 7, 8, 9 possible sums that are greater than 6 and even, okay, out of 36 possible sums. We can also explore that with some other ideas, like what is the probability of having an even sum knowing that the number has to be greater than 6. Now, knowing the number is greater than 6 totally changes my universe. So I have to think, okay, well, which sums are greater than 6? So if I go back here, this sum is, oops, wrong tool. This sum, there we go. This sum is greater than 6. That sum is greater than 6. This sum is greater than 6. All those red sums are greater than 6. And so what do we have? We have 1, 2, 3, 4, 5, 6, all added up. So what's that give me? 1 and 2 is 3, and 3 is 6, and 4 is 10, 15, 21. There are 21 possible sums that are greater than 6. How many of those are even? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9 of them are even. So that means I have 9 out of 21. Next thing we'll take a look at, what is the probability of being greater than 6? Okay, well, that's just our red ones here, right? There's the 6 plus 5 plus 4 plus 3 plus 2 plus 1. And I double check that adds up to 21. Let's see, 6 and 5 is 11, and 4 is 15, 16, 17, 18, 19, 20, 21. Yes, so there are 21 possible sums out of 36. And earlier, I stated the formula back here that the probability of A and B is equal to, nope, this one up here, the probability of A given B times the probability of B. Okay? And I have to use that if they're not independent. Independent means knowledge doesn't change stuff. And the knowledge of being even does change things. So what should be true then is that the probability of even given greater than 6 times the probability of given 6 should be equal to the and thing up there. So double check that. If I take 9 over 21 times 21 over 36, the 21s cancel, giving me 936, which is the and. And again, these take practice. So if you're new at probability, it's going to take some getting used to, even with all the experience. I have, every once in a while, I really have to think hard. Most of the time, actually, I have to really think hard. Something to consider here is often people will confuse the idea of and with the idea of knowledge given. And they are two different things. We do not, there's a relationship, but they're not necessarily equal. And we'll often confuse those, and we just have to think about it and play around with numbers. Let's try another example. Let's see, here's a good one. So marijuana is now legal in Oregon. And so I have a friend who's very excited about that. And so he wants to start a grow site. Cool, because it's legal to do so with all the right permits. On the other hand, he has another job right now, and at that job, he gets tested for using marijuana, and if they find he's using it, then he is unemployed. That's a problem. And so here's some data on a marijuana test to test if somebody has THC in their system in recent time. And so we're going to ask a few questions about this. So let's see. What is the probability that, let's say, M is a marijuana user and P is a test positive? That means a non-user would be M with a bar over it, and a negative test would be a P with a bar over it. Actually, let's reverse that. That sucks, because I'm using P for probability also. Let's use N as test for negative, then an N with a bar over it would be testing positive. So what's the probability that somebody is a marijuana user and they test negative? So that means we want to look at when those two conditions are met at the same time. So we have our marijuana users in this column. And I wanted to use the highlighter. There we go. In this column. And I have our test negative in this column. And those guys meet right here at the 5. So then what I believe is that there are 5 individuals in this study who used marijuana and tested negative out of a total of 300 in the study. Okay. So again, this is my main body of data right here, and then I have totals for each row and each column underneath. So that's the probability that somebody uses marijuana and tested negative. Okay. That's what we would call a false negative. Okay. The test should have brought up positive, it just didn't, right? Nothing's perfect. What is the probability that somebody tested negative knowing that they were a marijuana user? Now, knowing they're a marijuana user, right? So this is what I know. I can know that they use marijuana. So that's all I care about. Now, 120 of the people that were surveyed here used marijuana out of the 300. So that's my new piece of information, right? That's all that matters. Now, I'm hoping to find the ones that tested negative, okay? So of the marijuana users, 5 of them tested negative. So I believe the answer is 5 out of 120, whatever that reduces to, or you can make that into a percentage if that makes you happy. The formula given earlier says another way to count that probability, if you can't reason through it, is to try and find the probability of negative testers and marijuana users, that combination. Now, and is commutative. It doesn't matter whether I write M and N or N and M. Order is irrelevant. And then I divide that by my universe, the probability of knowing they use marijuana. Okay, so the probability that they're a negative, they tested negative and used marijuana, well, we already did that. That is 5 out of 300. Divide by the probability that they use marijuana. Well, there are 120 people that use marijuana in the survey, so the probability is 120 out of 300. And if I apply my little arithmetic jiggery-pokery to that, I get 5/300 times 300 over 150. 300s cancel conveniently, leaving me 5 over 150. Okay, same answer, 2 different ways to get it. One more problem, and then I'm going to shut up and go away. This is about the hardest part of the chapter. Let's take a look at our book. I thought this was an interesting problem that we can sort through. Studies show that about 1 woman in 7, it's about 1/7 is about 14.3%, who live to be 90 will develop breast cancer. Okay, suppose that of those women, so we know it's one of those women, they test negative 2% of the time. Okay, so that second sentence is a conditional probability. What's the probability they test negative knowing they're one of those 1/7 of the population that will develop breast cancer? Also suppose that the general population of women, the test for breast cancer is negative about 80% of the time. Let B be a woman who develops breast cancer. That's our first sentence. let N equal the test negative. That would be our third sentence. We want to know, and then suppose a woman was tested at random. We're going to answer some questions about this. So let's drag that into my notebook. New screen, clip. Okay, so B again, let's highlight that. In yellow is a woman who develops breast cancer, and N is a negative test. So then the probability of a woman developing breast cancer is 1/7. 1/7 as a decimal is 0.142857 repeating. It's kind of sad that I know that. No, it's kind of cute. It's nice repeating part. And if we rounded that to 0.1%, that would be approximately 14.3%. The probability that someone has, a woman in general, has a negative test is 85%. The 2% is the probability of having a negative test knowing that they're a woman who will develop breast cancer or has breast cancer, and that is the 2%. So that's my read. So let's check with what the authors of our book believe about this situation. So they want to know, what is the probability that a woman develops breast cancer? Okay, so that was our original. That should be 1/7. What is the probability that a woman tests negative? And that should be the 85%. And so probability of B, that a woman develops breast cancer, is about 14%, which is 1/7. Probability that a woman tests negative in general is 85%. Given that a woman has breast cancer, what is the probability that she tests negative? So let's compare that to the second sentence. Suppose that one of the women above that develop breast cancer, suppose that we have one of the women, a test is negative 2% of the time. Okay? I think those say the same thing. So that would be the probability of a negative test given that they develop breast cancer. Right? So probability of a negative test given that they have breast cancer, that's the 2%. All right, next. What is the probability that the woman has breast cancer and tests negative? Okay, so here's the tricky part. That kind of sounds like the one above. But again, this one says given. We already know they have breast cancer. So that changes what my denominator is. That changes the group of people I'm looking at. Right? What is the probability that a woman has breast cancer and tests negative? So let's write that down in my little notebook. So now I want to figure out, what is the probability that a woman has breast cancer and tests negative? And if having breast cancer and testing negative were independent, then I could just multiply probability number 1 here times probability number 2 and get an answer. But I don't know that. So we could double check it. If we multiplied 1/7 by 85, you can ask Google what that is. What is 1/7 of 85? And we get about 85%, 0.85. We get about 12%. Let's see, what was my point there? And I don't know what my point with that is. Anyway, let's write down the formula. Formula here says that this should be equal to the probability. Now there's 2 ways you can look at it. You could say it's the probability of B knowing N times the probability of N. Or you could say it's the probability of N knowing B times the probability of B. It turns out these guys wash out in the end. They're the same thing. One problem I have is I don't have that guy right there, so I can't use that method. So I'll have to look at this one right there. So here, if I don't think they're independent, so does knowing they have breast cancer change the probability of having a negative test? Well, yeah, it does, because these 2 guys right here aren't equal. Okay, so since those guys are not equal, that implies that we do not have independence. Knowing somebody has breast cancer affects how the test comes out. That's not exactly right, but it's close. All right, so these are not independent events. So that means to find this, I have to take that 2% and multiply it by my 1/7 and see what I get. So that's a different calculation than I did before. Let's hit enter on that one. So that was the 12%. Come on, Google. That's the wrong answer. The right answer should be 0.02 times 1/7 or divided by 7. And that is, if you turn that to a decimal, that's less than a whole percent. Okay, so, which is not the same as this probability right here. So more evidence that I don't have independent events. So that is approximately, let's see, let's copy that sucker. Copy, screen clipping. That's this guy right here. And if we change that into a percentage, we would shift the decimal point 2 places. So if I stated it to the nearest 1/10 of a percent, it would be 0.3%. If you wanted to take it farther, you could call it 0.29%. And you could keep going like that all day. Now let's check with the book. Where'd my book go? Right there, see if they agree with us. They say we have to multiply the probability of B times the probability of N given B, which is that 1/7 times 2%, and they're gonna take it to 100th of a percent here. All right, so I'm gonna stop this recording here. The biggest confusion people are gonna have is the difference between, say, N given B or B given N and the probability of N and B or B and N. So the condition and the intersection are confusing sometimes, and we just have to be really careful with language to figure that out. That's only one minor point in the whole chapter, so if you get it now, cool. If you don't, there's time to work on it. Have a good day, do good math, take care, bye-bye.